Welcome everyone. Let's get started with this here, shall we? So this is something that I'd like you to actually pause the video here and just try to work on this problem before you move on, okay? We have some parallel lines here, so I'm going to go ahead and mark those. We're told that ABC is 41 degrees and CDE is 38 degrees. And we want to calculate BCD out there. Looks like a really strange problem here. And in this situation, we're going to take a page out of my friend Morpheus's book. Free your mind here, because there's something missing. Okay, and I'd like you to consider drawing that in. So, considering the hint, there is something missing here, and it seems like we want to draw parallels to what already we've seen. Some of you might imagine that there might be other ways of doing this problem here, but consider this here. I've got lines like this here, right? These two lines are parallel, which means they're never going to meet. So we can try to draw a line that's parallel to both of them simultaneously. And we can also, and it seems like there's this point C in the middle here that's begging to be drawn through. So let me go ahead and sketch a new line like this here, ladies and gentlemen. Here's my line. I'm going to call this line FG. And we're going to create this line so that it's parallel to AB and DE here, right? So in something like this here, we can go ahead and put this together. So take a look at this here, right? Parallel lines, that's a 41-degree angle here, so that means this is alternate interior, and this is 41 as well, right? So if this is 41 degrees, BCF is an alternate interior angle to ABC here, so these both are 41. Similarly, we have a 38-degree angle down here, CDE, so by the same token, we have alternate interior angle, so DCF is 38 degrees as well, right? So we can kind of do something like this here, and we end up with something that looks like that, and therefore we know that the measure of angle BCD here is just 41 and 38 here, and that tells us it's 79 degrees. So this will work out pretty well. Now, this problem seems, once you see the trick behind it, you seem, oh wow, I'm surprised I didn't see this before. But, the philosopher, the mathematician may consider, okay, that's great. We drew in a line. I mean, it makes sense that it's there, but how do we know it exists? Because, this line here, we're assuming that, because there's two parallel lines, there's a space in between, and I can put a new line that will not intersect the other two. But how do I know I can do that? So that's actually a topic that was tackled back in the day by several mathematicians. And one of the most famous mathematicians who tackled this is this person here, which I think you're all very familiar with. We're going to be looking at this gentleman known as Euclid of Alexandria here. So, lived approximately around 300 BC, and I think many of you know about Euclid because he gives his name to the system of geometry that we're looking at right now. We're looking at Euclidean geometry. So as I mentioned back in the second unit here, Euclid wasn't necessarily a special mathematician in terms of his raw brain power or things like that. What made him so well known was the fact that he actually put this system together, this system of axioms and postulates and theorems here. He was the one who actually who argued for its use, and as a result, the system works the way it does. Now, he was able to build everything up from the little things. So he used a lot of the same postulates that we did. So a lot of the same undefined, the same primitive notions and the same axioms. But these are the 5 that he made very, very famous here. So Euclid's 5 postulates. I'm just going to run through each of these one at a time. So these are Euclid's 5 basic postulates here, and you're going to be seeing this a lot here. So the first postulate is that a line can be drawn connecting any 2 points, right? We're going to accept that this is true. It makes sense, right? If you have any 2 points, you can draw a line that goes between them. The second is that any line can be extended infinitely in any direction. So if I have a line like this here, so here's A and here's B, right? The first postulate guarantees us that I can draw a line like this, a line segment here, or a line like this here. If I have a line segment AB here, the second postulate guarantees us that I can extend it like this forever in that direction. And I can also extend it in this direction as well. So note that in this situation, that's our second postulate here. Our third postulate is that all right angles are congruent. I think we're all very familiar with that here. This is another well-known one that he was able to, that he assumed. The fourth one here, as you can see, is a unique circle could be drawn with given center and radius. So that means, basically, it's like, if you have a point here, let's call this C, and you have a given radius R. This basically tells us that there's one and only one circle that you can draw like this here that has the center C and has the radius R here, okay? Now, this last postulate here is a little bit weird, so I really want you to focus on this one. This one, he referred to this as what is known as the parallel postulate, or as we call it, Euclid's 5th. Given a line and a point not on that line, there exists exactly one line through the point parallel to the given line here. So notice how in something like this, first things first, this is a lot more complex, right? If you consider the first four, they were very, very straightforward. You could read them, and probably within half a second, you could understand, okay, I know what this postulate is trying to say. But this one takes a little bit of time to grok, doesn't it? It feels like you have to sort of put this together. The idea is that, again, we're considering a line here. Here's a line L, and here's a point P. So Euclid's fifth postulate, or the parallel postulate here, basically tells us that there is this blue line here that runs through P and is parallel to L. Not only does it exist, not only can we find that line, but it tells us that it's the only such line that exists here. Now, this postulate has a bit of a storied history amongst mathematicians. Euclid himself really didn't like this postulate. He kind of likened it to a sort of a necessary evil. It was something that he considered to be, he needed to use this for just some reason here. He tried to avoid using this if at all possible. And one thing that he wondered is it possible to get this postulate from the other four? And he tried for quite some time, and it turns out that the answer for that was no. He could not figure out why. And this is also something that mathematicians that are closer to the modern day, say around 1700 or 1800 or so, they actually also tried to consider this as well. Is it possible for us to prove this fifth postulate here, or is this fifth postulate sort of just there? And the conclusion that they came up with is that the fifth postulate is, again, it's just there. It's just sort of a necessary thing that needs to be done in this situation here. And we're not going to worry too much about that here. So note that these postulates here, again, we're going to use them, and we can just simply cite them by how we say this. So we can just say a line can be drawn connecting any 2 points, and things like this here. We're going to be using these postulates here, okay?